Hello everyone. In our heat transfer lecture series, we have already studied some concept of the steady heat transfer. Again in this chapter, we are going to study a new concept as the heat transfer from a finished surfaces. Suppose we consider a solid surface and heat will be transferred. It is by convection. That means some of the fluid will flow over that surfaces. In that, heat transfer is found out by using Newton's law of cooling. Okay, and the formula of Newton's of cooling we have given as q convection as is equal to h as ts minus T infinity. So here h is called as heat transfer coefficient, as is surface area, ts is surface temperature of solid, and T infinity is the temperature of a fluid flowing over that surfaces. Okay, now if we need to increase the heat transfer rate, what should we do? So for that, if you consider here, when Ts and T infinity are both the temperatures, solid temperature and the fluid temperature, if both are fixed one, then we have only two ways to increase the heat transfer rate. Okay, so in that, first we will consider about the Ah. H to H is heat transfer coefficient. To increase the convection heat transfer coefficient H, this may require the installation of pump or fan or replacing the existing one with the larger one. But this approach may or may not be practical, besides it may not be adequate. So if you consider about the heat transfer coefficient, it is dependent upon several properties of solid and the fluid flowing over that surfaces. Okay, so that's why to increase the heat transfer coefficient, we will use to increase the velocity of that fluid over that surfaces. But this is not adequate some of the concepts. So that's why we are not going to this concept. So we will go to the next one as AS. To increase the surface area AS, by attaching the surface, extended surfaces called the fins, made up of highly conductive materials such as aluminum. So that means if you increase a surface area of a solid one, and we already discussed about that, if we heat transfer rate is depend upon the surface area. If surface area goes on increasing, obviously heat transfer rate goes on increasing. Okay, so for that we will consider some examples here. So examples here we have given here. So presumed cooling fins on a dinosaur Stegosaurus. In dinosaur era, in that we can say that at 150 million years ago, some of the dinosaurs, just like a Stegosaurus, they have a bone-like structure over that back. What are these? We will consider that these are the for safety purposes. But actually, what will happen? The large amount of blood will be circulated over that bone structure. Then what will happen? The large amount of heat will be supplied to the surrounding medium. So that means this is for the heat transfer rate, to increase the heat transfer rate. So this is a very old example, but now if you see in our cars, we have used a radiator, and in that radiator, what will happen? Thin plate fins of a car radiator greatly increase the rate of heat transfer to the air. So in the radiator, what will happen? Hot water will flow through the pipes, and over the fin surfaces the air will be flow. Then what will happen? Due to the large amount of fins, the heat transfer rate will be increased, and that heat will be supplied to the air. So this is the good examples of the heat transfer through the extended surface, or we can say through the fins. Okay. Now next one, to find out the fin equation, what we have considered here? We have considered here a base we have considered here a base material. So this is a base material, and for that base material we have used a extended surface or the fin. So this is the fin. Okay, so we will consider the surface temperature of a base material as a T0. Okay, T0, or we can say as a TB also, T suffix B. Okay, we can say it is a base temperature. Okay, now next one out of that we will consider some of the element. So this pink area shows the element to find out the fin equation. Okay, then here we have used H is heat transfer coefficient, and T infinity is the surrounding fluid temperature which is going to flow over that fin surfaces. and the heat transfer may take place. Okay. Now, so for that, what we have used? So here we have used a fluid element, or sorry, volume element, and that volume element is available at a distance x from the base, and the delta x is the width of that volume element, and total length of the fin is considered as a capital L. Okay. Now here what we have indicate, so q conduction x, the heat transfer by the conduction from the base material to the volume element, it is considered as a q conduction x. Q convection, it is the convection heat transfer from the volume element to the surrounding, and q conduction x plus delta x, this is the conduction heat transfer will be carried from the volume element to the other part of the fins. Okay. For that we will consider the heat balance equation as the rate of heat conduction into the element at x. This is equal to the rate of heat conduction from the element at x plus delta x plus rate of heat conduction from the element. So that means we have given the equation as, we have given this is equation q conduction x is equal to q conduction at x plus delta x plus q convection. Okay. So in that we will find out the q convection equation as h in bracket p delta x multiplied with t minus t infinity. So here h is heat transfer coefficient and p is perimeter of the volume element, and delta x is the width of that volume element, t is, we can say, the temperature of the fin, and t infinity is the temperature of the fluid. Okay. Now if we substitute this formula in previous equation, what we will get, and substituting these values or rearranging this equation, we will get q conduction x plus delta x minus q conduction x divided by delta x. So we are now dividing this value with the delta x plus hp t minus t infinity, this is equal to 0. Now if you taking the limit as a delta x tends to 0, what we will get, this equation will be converted into derivative equation. So what is equation? So derivative of q conduction with respect to dx plus hp t minus t infinity. So here from this equation delta x will be cancelled because we are dividing delta x to this equation. So delta x is going to cancel. Okay. Now, so in this equation, d of q conduction with respect to dx plus hp t minus t infinity is equal to 0. Okay. So in this equation, if you substitute the conduction equation formula as q conduction is equal to minus k ac dt by dx. So this is called as Fourier law of heat conduction. This is called as Fourier law of heat conduction. And if you substitute this value in this equation, previous equation, what will get, d of dx in bracket k cross sectional area multiply with dt by dx, bracket complete, minus hp t minus t infinity is equal to 0. If you solve this, what will get equation as d square theta divided by dx square minus m square theta is equal to 0. So in that equation we have substitute theta as, theta is equal to t minus t infinity. Okay. And here if you taking kac as common, and we'll get, we have write down here m square. So what is the value of m square? M square is equal to hp divided by kac. Okay. So we will get here differential equation, second order differential equation. So this is our second order differential equation, and if you solve this equation, we are getting the solution as, there are two solutions we are getting in the terms of e raised to mx and e raised to minus mx. So here if you solve this equation, we will get theta of x is equal to c1 e raised to mx plus c2 e raised to minus mx. Here c1 and c2 are the constants, arbitrary constants. We can find out these values of c1 and c2 by using two boundary conditions. So out of that, first boundary condition we have considered here as, first boundary condition we have taken the temperature at the base, temperature reference at the base. Okay. So that we have considered here at the base Tb minus T infinity. So theta of substituting x is equal to 0, theta of 0 is equal to dB minus d infinity. So this is the first boundary condition. We can substitute value of x is equal to 0. Okay, now next one, to find out the another boundary condition. So what we have the basic formula for the fin. We have taken as theta of x is equal to c1 e raised to mx plus c2 e raised to minus mx. So this is our basic formula to find out the temperature difference in the fin. Okay, now here there are several concepts to find out the heat transport through the extended surfaces. There are the four conditions. Out of the four conditions, we have considered first one as infinitely long fin. That means length of the fin will be very much long. So in that, another boundary condition, first boundary condition is same as the previous one. Same as previous one, which one denoted here. Theta of 0 is equal to theta of b is equal to tb minus t infinity. Now if we substitute x is equal to L, and L we have already denoted as the infinitely long fin, that means L tends to infinity. So L tends to infinity. If you substitute in this equation, what you will get, theta of L is equal to TL minus T infinity is equal to 0. Now to solve this equation, which equation? So this equation, theta of x is equal to c1 e raised to mx plus c2 e raised to minus mx. If you substitute x is equal to 0, then what we will find out the value of one of the constant, and if we substitute x is equal to L or x is equal to infinity, then we find out the another constant. Okay, now for this concept, for infinitely long concept, what will happen if we substitute the solution? We are not getting the e raised to mx. If you substitute x is equal to infinity, that term becomes 0. So that's why it is very difficult to find out the value. That means we have the only solution for the very infinitely long fin, these c2 e raised to minus mx or e raised to minus mx. Now if we substitute the values, we will find out the solution as theta of x minus t infinity divided by theta of b minus t infinity is equal to e raised to minus mx. So what we are getting, if you solve this equation as theta of x is equal to c2 e raised to minus mx. Okay, so in that if you substitute x is equal to 0, then e raised to mx is 1, and theta of x we already find out at 0 is tb minus t infinity. So from that we will find out the arbitrary constant c2 as value, the tb t of b minus t infinity, and we substitute all these values in our equation theta of x, then what we are getting, theta of x is equal to, so c2 value we already find out, tb minus t infinity multiply with e raised to minus mx. So in that formula, from that formula we can find out, so theta of x is t of x minus t infinity. So from that formula we will find out, this is our equation. So theta of x, t of x minus t infinity divided by tb minus t infinity is equal to e raised to minus mx. Okay. Now, so here what is theta? Theta is t minus t infinity, already we have discussed, and m is equal to square root hp divided by kc. That means m square is equal to hp divided by kc. Okay. So in that, from that we can find out the heat transfer rate or steady rate of heat transfer from the entire fin q long is equal to minus kc dt divided by dx at x is equal to 0, and that why if you substitute the values, what we are getting, square root hp divided by hp into kc in bracket tb minus t infinity. So this is the formula to find out the heat transfer rate from a very long fin, and in this formula we can find out a temperature at any point on the fin, temperature on any point of the fin. okay, if we know the value of x. Now next one, we will see another concept as sorry. So here at, if you see the graph will be found out, the temperature will be reduced from Tb to the T infinity as in this direction in the exponential curve. Okay. So under steady condition, heat transfer from the exposed surfaces of the fin is equal to the heat conduction to the fin at the base. Okay. So we have the formula Q of fin is equal to integration of area of fin h Tx minus T infinity multiply with d of area of fin is equal to integration of area of fin h theta of x d of area of fin. Okay. Now next one. Now second concept as the negligible heat loss from the fin tip, or we can say adiabatic fin tip or Q fin tip is equal to 0. That means this concept as from the fin tip there is no heat transfer will be take place. Okay. So fins are not likely to be so long that their temperature approaches the surrounding temperature at the tip. A more realistic assumption is for the heat transfer from the fin tip to be negligible, since the surface area of the fin tip is usually negligible fraction of the total fin area. Okay. So for that we have the boundary condition d theta by dx at x is equal to 0, x is equal to L is equal to 0. Okay. So this is our boundary condition. First boundary condition is as it is, if substitute value of x is equal to 0, Tb minus T infinity. So theta of 0 is equal to Tb minus T infinity. This is our first boundary condition. And second boundary condition, at the fin tip d theta by dx at x is equal to 0 is equal to 0. That means there is no heat transfer. If you substitute this formula, then what we will get? We will get the temperature distribution over that fins as T of x minus T infinity divided by Tb minus T infinity is equal to cos m L minus x divided by cos of m multiply with L. Okay. So this formula will be used to find out the temperature distribution for a negligible heat loss from the fin tip or the adiabatic fin tip condition, and the heat transfer rate from the entire fin will be find out for Q adiabatic tip is equal to minus KAC dt by dx at x is equal to 0. So that means square root HP KAC in bracket Tb minus T infinity multiply with hyperbolic tan multiply with ml. So this is for the negligible heat loss from the fin tip. Now next one, specified temperature of the fin tip. So second concept that if you consider a fin tip have a particular temperature, a particular constant temperature is available, then what we have? In this case, the temperature at the end of the fin or the fin tip is fixed at a specified temperature as TL. Okay. So this case could be considered as a generalization of the case of infinitely long fin where the fin tip temperature was fixed at T infinity. Okay. So boundary condition at fin tip is equal to T theta of L is equal to theta L is equal to TL minus T infinity. Okay. So if we solve this one, what we will get? We are getting the temperature distribution over this fin as T of x minus T infinity divided by Tb minus T infinity is equal to in bracket TL minus T infinity divided by Tb minus T infinity multiply with hyperbolic sign mx plus hyperbolic sign m multiply with L minus x and whole divided by hyperbolic sign m into L. So from that equation we will get a temperature distribution over a fin. Okay. And if we substitute this one, or by that we can find out this total amount of heat transfer from a specified fin temperature condition. Q specified fin temperature is equal to minus KAC dt divided by dx at x is equal to 0. That means at the base. So this is equal to square root HP KAC multiply with Tb minus T infinity multiply with hyperbolic cos ml minus TL minus T infinity divided by TB minus T infinity divided by hyperbolic sin ml. And last condition is convection from the fin tip. So last condition we will consider if the from the fin tip convection heat transfer will be takes place. So the fin tips in practice are exposed to the surrounding, and thus the proper boundary condition for the fin tip is convection that may also include the effect of radiation. Consider the base of convection only at the tip. The condition at the fin tip can be obtained from an energy balance at the fin tip. So we will consider heat balance as Q conduction is equal to Q convection. Okay, here. So boundary condition at the fin tip as minus KAC dt by dx at x is equal to L, that means at the total length of the pin. We will consider conduction heat transfer. This conduction heat transfer is equal to convection heat transfer, HAC multiply with TL minus T infinity. So TL means the temperature of the fin available at the fin tip minus T infinity. T infinity is surrounding temperature. Okay. So from that we will get the values for the C1 and C2, and from substituting these values we will get the temperature distribution for this convection heat from fin tip conditions as T of x minus T infinity. So here the temperature distribution for this condition. So Tx minus T infinity divided by Tb minus T infinity is equal to hyperbolic cos m multiply with L minus x plus h by mk. So here k is the thermal conductivity, hyperbolic sin m multiply with L minus x divided by hyperbolic cos ml plus in bracket h by mk multiply with hyperbolic sin m into L. After find out this temperature distribution, we can find out a total amount of heat transfer from this fin as Q convection fin tip is equal to minus KC dt by dx at x is equal to 0, and this is our formula. Q convection is equal to, or the heat transfer from that fin is equal to square root HPKAC multiply with TB minus T infinity. So sin multiply with sin hyperbolic sin ml plus h by mk multiply with hyperbolic cos ml total divided by hyperbolic cos ml plus h by mk hyperbolic sin ml. Okay. So here a practical way of accounting for the heat loss from the fin tip is to replace the fin length capital L in the relation to the insulated tip case by corrected length. So defined as LC is equal to L plus AC divided by P. So corrected length we will consider total length plus cross sectional area divided by perimeter of that fin. Okay. So if you consider any fin and it is corrected for the insulated tip condition, so we can consider as L plus AC divided by P. So for rectangular fin, LC corrected length is equal to total length plus T divided by 2. So T is the thickness of the rectangular fins, and for cylindrical fins corrected length is equal to L plus D by 4. So where D is diameter of cylindrical fins. So it is simple way to find out the heat transfer rate by using a insulated fin tip condition. So for that we have given a corrected fin length. Okay. Now next one is the fin efficiency. So what is our fin efficiency? Fin efficiency will consider if fin will be attached to the base material and if heat transfer will be takes place. And to find out the fin efficiency, what we consider if surface without the fins and surface with the fins. Okay. So how much amount of heat transfer will be takes place from the base material when there is no fin, and if surface material is base material is attached to the fin condition. From that one, so So we know that the maximum amount of heat transfer will be takes place when the total fin is available at the base temperature. So for that we have the figure. If you consider total fin is having the surface temperature as a base temperature. So in the example we have given as a 80 degrees Celsius surface temperature over entire the fin. But in actual condition, this surface base temperature will be reduced up to the fin temperature. So for that, fin temperature will consider as fin efficiency will be considered as Q of fin maximum. Q of fin maximum is equal to H of fin in bracket TB minus T infinity. So zero thermal resistance or the infinite thermal conductivity. Temperature of fin is equal to temperature of base. So efficiency of fin we will consider as actual heat transfer rate from the fin divided by ideal heat transfer rate from the fin if the entire fin were at the base temperature. Okay, so by using this formula we can find out here the efficiency of fin is equal to efficiency of fin multiply with heat transfer rate for a maximum condition, maximum heat transfer rate. So this is equal to efficiency of fin multiply with H area of fin multiply with TB minus T infinity. So from that formula we can directly find out the heat transfer rate of the fin if we know the efficiency of fin. So for very long fin, what is the efficiency? Efficiency of long fin is equal to Q of fin divided by Q of fin maximum is equal to square root HPKAC multiply with TB minus T infinity divided by H area of fin multiply with TB minus T infinity. So if we solve this, we will get 1 upon L square root KAC divided by HP, and this is equal to 1 upon ml. So efficiency of very long fin is 1 upon ml. So what is m? M is square root of HP divided by KAC. Okay. Now adiabatic fin tip condition. Adiabatic fin tip condition, we have heat transfer rate, actual heat transfer rate divided by maximum possible heat transfer rate is equal to square root HPKAC multiply with TB minus T infinity hyperbolic tan into ml divided by H area of fin TB minus T infinity. And if we solve this, we are getting hyperbolic tan ml divided by ml. So this is the efficiency of adiabatic fin tip condition. Okay. Now we will see the fin effectiveness. So fin effectiveness is equal to effectiveness of fin, epsilon will be denoted as a fin effectiveness is equal to Q of fin divided by Q of no fin. That means we have the heat transfer rate from the fin for a base area AB divided by heat transfer rate from the surface area of AB. So actual heat transfer rate from the fin divided by, if the fin is not there, how much amount of heat transfer takes place, that will find out from the heat transfer rate from the base area. So that means efficiency of fin is equal to heat transfer rate from the fin divided by heat transfer rate from the base material if there is no fin. Okay, so this is the formula. So for very long fin we can find out the effectiveness of fin is equal to square root Kp divided by HAC. So what is effectiveness? Effectiveness, if the ratio of, it is the ratio of a heat transfer rate from the fin to the heat transfer rate when there is no fin is available. Okay. Okay. So these are some concepts. To total rate of heat transfer you can find out as a Q total is equal to Q of unfin plus Q of fin. So unfin area and the fin area, if we take the heat transfer rate from this one, we can find out the total amount of heat transfer from that surfaces. Okay. So effectiveness of fin overall is equal to Q of total of fin divided by Q of total with no fin. Okay. So from that formula we can find out the effectiveness of overall surface. Thank you.